Hi there. In this video I'm going to try to explain the cardiac cycle and the very commonly seen cardiac cycle graph. Okay. When we're doing this and when any question on the cardiac cycle, there are always three things to consider and three things to comment on in your responses. Firstly, they are the pressure differences. So this needs to be a comparative statement. Something along the lines of the pressure in the atria is greater than the pressure in the ventricles. Next, that pressure difference will have an effect on the valves. So you name the valves and how that affects it. They're either open or closed. So if the pressure in the atria is greater than the pressure in the ventricle, the atrioventricular valves, perhaps the bicuspid valve, is open. Lastly, you make a comment on the direction of the blood. So let's just go through all of those things. If the pressure in the atrium is greater than the pressure in the ventricles, the atrioventricular valves will be open, the blood will flow from the atria and into the ventricle. Now this can be demonstrated in a number of different ways, and one common way is with the use of a graph which is similar to this one that I'm going to draw on the board. You've got this graph on page 4 of the Mass Transport in Animals booklet, and then there is a similar one that I'm sort of taking the data from in question 3 in the question booklet. Okay, so I'm going to use a combination of the graph on page 4 in the notes and some of the rough data. It's going to be rough because I'm going to be drawing it on the board from question 3 in the question booklet. Okay, just to begin with, I would advise all students to colour code this diagram on page 4 in the notes. And to do that, if you have a look at the top section of this graph, it is similar to the one that I have on the board. It shows on the x-axis the time. So the time from 0 to 0.8 seconds. And if you have a look at some other graphs, for example the one on question 3 in the question booklet, that might extend beyond 0.8, perhaps 0.9, perhaps up to a second. Okay, on the y-axis we have the pressure, and that is the pressure measured in one of 3 places. It could be the pressure in the atria, and on my graph I'm going to show the pressure in the atria in green and use a green line. It could be the pressure in the ventricle, and on my graph that's going to be in blue, or it could be the pressure in the aorta. And therefore, if it's the aorta, this is the left ventricle and the left atria. But I'm not going to repeat that. Okay, so let's have a look at what's happening at each stage during the cardiac cycle, starting from 0 to 0.1 seconds. Okay, now if you look carefully at your graph, and after you've colour-coded it, this will be much easier. You will see in the first 0.1 seconds that the pressure in the atria is greater than the pressure in the ventricle. So that is that first comment, okay? Thinking about what we always comment on between 0 and 0.1 seconds, we talk about a pressure difference. The pressure in the atria is greater than the pressure in the ventricle. Therefore, if the pressure in the atria is greater than the ventricle, well, the atrioventricular valves will be open. We've made a comment now on the valves. And the blood will flow from the atria down that pressure gradient into the ventricles. And that continues as long as the pressure in the atria is greater than the pressure in the ventricle. But you'll notice at 0.1 that the pressure in the ventricle begins to increase. Okay? Something like this. I'm just going to stop it there for now. And we find that at 0.1, the pressure in the ventricle becomes greater than the pressure in the atria. And we get a crossover at 0.1 seconds, where the pressure in the ventricle is now greater than the pressure in the atria. So there's our comment on the pressure difference. If that happens, the atrioventricular valves will close. Comment on the valves. At this stage, and I'll explain a little bit more in a second why this is, but the blood will be flowing, there is no blood flow. The blood is just remaining in the ventricle, because that only changes at, and on your graph, and on my graph it's a little bit difficult to draw, but it's approximately 0.15, perhaps 0.14 seconds. So now we need to consider the pressure in the aorta. So we begin with the pressure in the aorta, according to the graph on question 3, it's just below 12. Okay, and that pressure decreases, something like this. This is a little bit approximate because I'm just drawing it by hand on the graph. But at about, or on your graph, at 0.15 or 0.14 seconds, the contraction of the ventricle means that the pressure in that ventricle is increasing. And at 0.14 seconds, they overlap, and now the pressure in the ventricle is greater than the pressure in the aorta. There's our comment on the pressure difference. If the pressure in the ventricle is greater than the pressure in the aorta, the semilunar valves, the aortic semilunar valves, will open. And as long as the pressure in the ventricle is greater than the pressure in the aorta, blood will flow from the ventricle and into the aorta. So there's that third comment on the direction of the blood flow. And if you look carefully at your graph, you'll see that that continues until 0.4 seconds. So at that stage, my red line on this graph that I'm drawing here is below the blue line, meaning that the pressure in the ventricle is greater than the pressure in the aorta. At 0.4 seconds, they overlap. Okay, and wherever you see an overlap, that's where a valve opens or closes. Now in this case, if the pressure in the ventricle after 0.4 seconds is lower than the pressure in the aorta, okay, so that's our comment on the pressure difference. The higher pressure in the aorta will cause the semilunar valves to close. Comment on the valves. The blood will no longer be able to flow from the ventricle and into the aorta. Comment on the direction of the blood flow. Okay, now this period is, if you have a look at the top of your graph, from 0.4 seconds, this is the period of diastole, when the contraction in the, or when the ventricles and the atria have relaxed. So the pressure continues to decrease until about 0.5 seconds. I'm going to show that down down here. Ooh. The best line I've ever drawn. Anyway, so at this stage, the pressure in the aorta is greater than the pressure in the ventricle, so those semilunar valves remain closed. If we go back now to looking at what's happening in the atria, until this stage, the pressure in the ventricles will be much greater than the atria, and so the atrioventricular valves have been closed. There's been no blood flow backwards from the ventricle to the atria. What we notice with the pressure in the atria, the pressure changes in the atria, it actually falls during ventricular systole, when the ventricles are contracting. Pressure in the atria actually falls below 0. If you have a look on question 3, the graph on question 3, it drops down to about -1 kilopascals. Okay, so this is below 0, and then it starts to increase again, and eventually, at about 0.5 seconds, the pressure in the atria is greater than the pressure in the ventricle. So now, there's a comment on the pressure difference. If the pressure in the atria is greater than the pressure in the ventricle, the atrioventricular valves will be open and blood will flow from the atria and into the ventricles. Okay, and then that continues throughout diastole with the pressure. I'm going to show it like that, with the pressure in the atria being greater than the pressure in the ventricle. And then at this stage, at 0.8, now you can't actually see it from the graph on page 4 of your notes, but you can see on the graph on page 3 in the, on question 3 in the question booklet, this is the beginning of the next cycle. And actually, if we add another 0.1 of a second, so maybe up to 0.9 on our graph here, we will see that at 0.9 we get a repeat. We get a repeat of what's happened at 0.1, where the pressure in the ventricle has increased again due to ventricular systole. Pressure in the ventricle then exceeds the pressure, is greater than the pressure in the atria. Comment on there. Atrioventricular valves close again, and the blood, well, at this stage is remaining in the ventricle until eventually it will exceed the aorta, or the pressure in the aorta. Just to return to that pressure in the aorta, you might notice that after those semilunar valves close, there's a little lump, an increase in the pressure in the aorta before it starts to gradually fall back down again. I guess it should fall down to the same point. I'll show you that down like that. Okay, now this little lump here, this increased or short period of increase in pressure, is due to the elastic recoil in the aorta. So the walls of the aorta contain elastic tissue. They stretch as blood moves into it and then recoil. And that recoil helps to close the semilunar valve, but it also forces the blood away from the heart, through the aorta, and to the rest of the body. Okay, so just to reiterate, the really important features to look for are the pressure differences. Use the graph, use the lines on the graph to see where the highest and where the lower pressures are. We know that blood can only flow from the atria to the ventricles and then from the ventricles to the aorta. Okay? The only thing that stops them from going the opposite way are the valves. So if we know the pressure difference, if we know that the pressure in the atria is greater than the ventricle, the only direction it can move is from the atria to the ventricle. During this period, between 0.1 and 0.4, so between here and here, the pressure in the ventricle is greater than the atria, so the atrioventricular valves must be closed. However, it's not greater than the aorta, so it's just building. The pressure is just building as that ventricular systole continues, till eventually, at about 0.14, 0.15, the pressure in the ventricle becomes greater than the aorta. Okay, so always consider the pressure differences. Always consider the valves. Another thing to note is each time we get a crossover of two lines, something has happened at a valve. Okay? So, here where the pressure in the ventricle becomes greater than the atria, the AV valves must close. Here where the pressure in the ventricle becomes greater than the aorta, the semilunar valves must open. And then the opposite later. So here, aorta greater than the ventricle, so the semilunar will close. Here, the atria greater than the ventricle, the AV valves open. One last thing I'd like to say is sometimes on the graph, as it is in the graph on question 3 in your question booklet, you'll be expected to determine the period for one cardiac cycle. So the period of one cardiac cycle can be found by looking for a repeating pattern. Now, I tend to do that by looking for the first time that the pressure in the ventricle becomes greater than the pressure in the atria. Because often in the graph, they will show two periods where we get this crossover. So from here to here is one cardiac cycle, one repetition. That time then becomes 0.9 minus 0.1, so the time for one cycle equals 0.8 seconds. Okay? With that, we can now calculate the heart rate. So to calculate the heart rate is the time in 1 minute, or 60 seconds, divided by the time for one cycle. Okay, so 60 in this example, 60 over 0.8 equals 75 beats per minute. Okay, and often that time for one cycle is 0.8 seconds if it's a human. Right, I hope that's helpful. Thanks very much.